All right, let's talk about current, voltage, and resistance. Now, current and voltage. Let's look back at what we talked about a little bit earlier in the electricity unit. When we did our introduction, we said there are two things that will affect what an energy source, like a battery, is able to power. Those two things are, number one, how many electrons it can produce every second, and that is the current. And number two, how strong those electrons are, which is the voltage. Now, we're going to talk a bit today about what those two things are in a little bit more detail. So the first one is what's called the electric current. And the electric current is simply the flow rate of electrons as they pass through a wire. Now, the amount of charge, or the number of electrons, which is also known as Q, that pass through a wire per unit of time in seconds. Now, the symbol for current is I. Now, I know that may seem a bit confusing. Unfortunately, that is what it is, so you're going to have to just get used to it. The units for measuring current are what are called amperes, and the symbol for that is A. So electric current, the symbol is I, and it is measured in amperes. Now, what do we measure current with? Well, we use it using a tool that is called an ammeter. And what that does is it measures the amount of current flowing past a single point in a circuit. It is basically going to act as a counter. Now, it is going to be connected in series with the circuit, which means it has to be part of the electron pathway. Electrons actually have to pass through the ammeter in order for it to be able to count it. So, for example, we have here a circuit diagram, which you should be familiar with these symbols now. We have a single-celled battery here, we have a lamp, and we have this circle with an A in it, and that represents the ammeter. So that will actually measure the current at that exact point in the circuit. It will count how many electrons go by every second right here. Now, we could move it, we could put it over here, or we could put it over here, we could put it over here. We can put this ammeter anywhere in the circuit and it will measure the current at that specific point. Now, the other thing we were talking about today is voltage. That is also known as potential difference. You will also see that called electric potential. There are a number of different terms that you can see for it that are typically used interchangeably. Some of them can be slightly different from each other as far as the definition goes, but realistically for what we're going to be looking at, we can pretty much use them all the same way. Now, the voltage could refer to one of two things. Number one, the gain in energy provided to electrons when passing through a power source. So if we have a battery and we have electrons have come back into them from the circuit, when they go through the battery, they will gain energy, right? So that gain in energy is the voltage that is given to each electron, and it is the voltage of the battery. So if I said a battery was a 9-volt battery, that means that every electron that goes through the battery will get 9 volts of energy given to it, right? The other way it's used is the loss of energy caused by electrical resistance when electrons flow through a load. In other words, when electrons go through something like a light bulb or a motor, they are going to lose energy to power that particular load. So it could be lighting the light bulb, it could be turning the motor, but that loss of energy is what's called its voltage, all right? Now, that happens because the load will resist the flow of electrons. So we're going to get into what's called resistance in a minute. So again, the gain in energy is what's going to happen at the battery. That's the voltage of the battery. That is the amount of energy given to every electron. The loss of energy is going to occur at any load. The symbol for voltage is V, conveniently, and the units are what are called volts, which again is quite convenient, and the symbol for volts is V. Now, an analogy that's often given for what voltage is the use of a water pump, for example. So a battery is going to give energy to electrons and then send them out into the wire. Now, those electrons will travel through the wire and then they'll hit some sort of load, a fan, for example, and that will cause the fan to turn. And then the electrons will return back to the battery. And at that point, the battery will give them more energy again, and they can go back out into the circuit. Now, the same type of idea can happen in a water pump. So a water pump can provide energy to water by pushing it up an incline. So when that water gets pushed up to a higher position, it can flow and then fall through or past a water wheel. All right. And when it does that, it can spin the water wheel. And that means that this energy that is given to the water from the pump is now transferred to the water wheel, and then it returns back to the water pump. Now this is why you'll sometimes see voltage referred to as electric potential, because that energy that has been given to electrons when they pass through the battery has the potential to be used to turn a wheel, just like the energy that is given to water from a water pump is also called potential energy. Now, if you happen to take a senior level physics course, you'll learn about what is called kinetic and potential energies. And potential energy simply means stored energy. It means energy that is held within, it could be within bonds in a molecule. It could be because an object is being held up at a high altitude and is being held against gravity and can fall and turn a wheel, like in this example. All right, or it could mean such as in this case, the potential energy given to an electron that could be used to turn a fan. Okay. Now, voltage is going to be measured with a tool that is called a voltmeter. Now, that is going to measure the drop in electrical energy or the pressure between 2 points in a circuit. So an ammeter had to be put into the circuit, and it just measures exactly what is happening at that exact point. A voltmeter will actually measure the difference between two different spots in a circuit. Now, the voltmeter, that has to be connected in parallel, and that is because it isn't going to be taking electrons out of the circuit. It is simply going to be measuring on two different points in the circuit. Right? So the way you would attach it would be, for example, if I wanted to measure the voltage of this battery, I would attach 1 point here and 1 point here, and the voltage would tell me what is the difference between here and here. How much energy has changed in electrons between this point and this point. All right, so the voltmeter is going to show the drop in energy from this point to this point, because it is going to be consumed by this light bulb. All right. Now, let's take a quick look before we look at resistance at what that can look like in a circuit. So I have here a simple circuit. I've got a battery here with electrons traveling out, passing through this light bulb along, and then it hits this object right here. Now, if you look over on the right hand side, you can see there are a couple of tools we can use. There's a voltmeter and an ammeter. I've already put the ammeter into the circuit, and right now it's saying the current is 0.90 amps. All right, so those electrons continue through here and back into the battery. Notice that it is in series with the circuit. All right, it is in the circuit. It is part of the circuit. So that means if I were to disconnect this ammeter, the circuit's going to stop because there's now no pathway for those electrons to pass. Now I can do this and reconnect it, and now we've got a complete circuit. And so over here, the current was 0.90 amps. What happens if I put it here? If I were to check what the current is at this position, make a prediction. What do you think the current should be at that spot? Well, hope you have your answer. Connect it there, and we get an answer of 0.90 amps. Right? And I can move it somewhere else. Right? I will cut it out of here. I can reconnect this, and that will start up again. If I cut my wire here and add in my ammeter, we can see it gives a measurement of 0.90 amps. All right, so I can place this ammeter anywhere within the circuit that I'd like. So that's first little tool that we can use. The second is our voltmeter. Now, you can see the voltmeter has a display here, and it's got two wires coming off. One is black, one is red. So what will happen is we can use these two wires to measure the potential difference between 2 points in the circuit. So let's say I want to check what is the difference between here and here. And if I do that, what I get is an answer of 9 volts. And that tells me that between here and here, so in this lamp, the voltage drop is 9 volts. That tells me that this lamp has consumed 9 volts of energy. Right? Now what happens if I go from here to here? Well, it's reading 0, and that's because the ammeter isn't actually using up any energy. If I try it from here to here, same thing. The wire isn't consuming any of the energy of the electrons. Now, in reality, they would. There would be a slight loss of voltage as electrons travel through a wire. And that's why you can't just send electricity on a wire across the world. All right? There are limits to how far electricity can travel in a wire. But if we want to just keep it simple, we can say that these wires, for the most part, don't really consume a lot of energy. Now, this light bulb has a voltage of 9 volts. What do you think the voltage of the battery is? Well, if I take this and put it here and put it here, we get an answer of negative 9 volts. Right? That means that the electrons are actually gaining energy. Right? So you notice it's the opposite of what was in the lamp. So if I check right before with the black and right after with the red, I get 9 volts for the lamp. And if I check right before the battery with the black and right after the battery with the red, I get negative 9 volts. And that is because in the battery, they are gaining energy, and then in the lamp, they are losing energy. All right? Now, something to notice. If an electron gains 9 volts of energy before it leaves the battery and travels along, and then loses 9 volts here, how many volts of energy does it have when it gets back to the battery? Well, if you're really paying attention, you should notice that it should now have none. So it gained 9 in the battery, it lost 9 as it came back after it went through the lamp. Now, what do you think will happen if we add another light bulb in? Well, let's find out. So let's cut this bulb cut this wire right here, and we're going to add another light bulb in. And let's check to see what happens to all of our numbers. Well, right away you can see that the current is now 0.45 amps. By adding another light bulb, we've slowed down the number of electrons that can pass through every second. All right? Now let's take a look at our battery again. So our battery hasn't changed. It's still the same battery. So it's still going to give every electron 9 volts of energy. But what do you think the voltage of those lamps are? All right, I'll give you a second to think about that. The likelihood is you've come up with one of two answers. Answer number 1 is the battery is 9 volts, so each of the lamps is still 9 volts. The other option is that each of the lamps gets half of the energy. And that's actually what's going to happen. These are identical lamps. They are the same as each other. They are going to share the energy of the electrons as they go around the circuit. So this one is 4.5 volts, and this one is 4.5 volts. And here's why. The basic rule is this. In an electric circuit, when electrons leave the battery, they have a full amount of charge from that battery. They have a full amount of voltage or potential energy. Whatever the voltage of the battery is, those electrons have to use it up before they get back. When they return to the battery, they will have 0 volts of energy left. All right? So if there's only one load in the circuit, all of the energy goes to that load. If there's more than one load, that energy gets split between each of the loads in in the circuit. Okay, so let's go back. Now, that's voltage and that's current. What about resistance? Now, I mentioned earlier that the loads within a circuit are going to resist the flow of electrons through it, and resistance is simply the measure of that substance's ability to do that. All right. So any object, any load in a circuit is going to slow down the flow of electrons, and resistance is just a measure of that ability. All right. So conductors, things like wires, typically have a very low resistance, which is why we want to use them in an electric circuit. Insulators, on the other hand, have an extremely high resistance. All right, so they slow down electrons significantly. Now, a load in a circuit is typically going to fall somewhere in between. There are some loads that have a very low resistance. There are some loads that will have a very high resistance. Now, when the flow of electrons is slowed by a load, the energy is used up by the load. So it's going to be consumed or converted into heat or light or motion, as in like a fan. The symbol for resistance is R, and the units that we're measuring it in are called ohms. And the symbol for it just looks like a kind of a horseshoe. All right. That's it for this one. There are a couple of videos that I'd like you to watch. There will be links posted to these with the video. The slideshow, you're also able to click on the links and watch it from there.